Now let us look at how to do data mining with another popular form of data that is coming up in recent times, that is the multimedia data. And let's multimedia itself is not just represents one type. There can be wide range of data that's referred to as multimedia. We'll look at some of the challenges with respect to handling the multimedia data in a brief way. The multimedia database may contain the audio, video, image, the graphics, or even the text and the markup languages. So these kind of data is becoming very popular because of the widespread use of the audio and video equipment, and which is also widely shared because of the social networks. If we look at a popular multimedia database, it's a NASA's Earth Observation System. And there are several other the image databases such as that represent the medical imaging, etc. And when we were looking at the multimedia data, if we want to do the mining and find patterns or to group the elements, one thing that we need to understand is how to find two elements which are similar. That is to say, two pictures, two videos, or two of these multimedia elements which are similar. So broadly there are two approaches. One is we can make a description based approach. So here what we do is that for each one of these item or object, we are going to assign some keywords such as caption or size or time of creation or the place of creation or the author, etc. So that can be one approach whereby we differentiate the objects using the description. But this requires that somebody needs to attach those keywords or captions to each one of the data elements. And that may have to be done manually, so it is going to be a labor intensive. And if we try to do it in an automated way, then we may not get good quality results because we are trying to give a right caption. So we do not know such software which can create a right caption for each one of these images. Other approach is the content-based approach, where we are looking at the picture itself or the multimedia item itself as the data. And we are capturing the images. For example, if it is an image, we are looking at the color. But if it is a audio, we will possibly look at the frequency or the volume. So we are going to find out the characteristics of the multimedia object, and thereby we identify the similarity. And when we are doing, let's say for an image database, a content-based retrieval, so then we can take again there are two approaches. One is that we can give a sample image and say that I would like to get all the images which are similar to this image. Or the other approach will be that for the image we would have extracted some of the characteristics such as the color or the layout, etc. And then we may use those features to give a specification and ask for the images which match those specifications. So when we are trying to identify the images or the multimedia objects through the features, then we may consider the possibility of creating a signature for each one of those multimedia objects. Let's say we are talking about images. Then for an image, the signature may be based on the color itself. So here we will not be concerned about the shape, location, texture, etc. So this type of a signature, if we create, it's easy for us to find out some queries. For example, a e-commerce website which is selling, let's say, millions of items, and then it has the pictures of all of the items that it sells. Then it can find out how many yellow items that we have sold, because here we have characterized the images based on the color. but it will not help us finding out the more sophisticated elements or the insight into the database. Otherwise, we can create a multi-feature based signature. There we will be using, beyond color, we can also use the shape, location, texture, etc. It's more difficult to create such a signature, but that helps us mine for many more characteristics with respect to multimedia data. We may also take a wavelet approach. Wavelet approach, what it does is that it is going to discretize many of the elements, and it is also going to consider, also it does a kind of compression whereby it only focuses on the important characteristics of the multimedia object. And if we can create that signature, such a wavelet based signature, we are likely to be more efficient with respect to processing. But some accuracy loss may be there depending on the kind of wavelets that we have used, and also the size that we had retained. When we have such multimedia data, we may resort to multidimensional analysis. And a multidimensional analysis can be based on the numerous characterization that we do for each one of these multimedia objects. Let's say we are talking about images. So we may have the dimensions that represent color, then texture and shape. And then like the way we do a multidimensional analysis or build a cube for business data, to understand, let's say, the sales which are across the geographies or across the products, etc. In this case, for a multimedia database also, we can create these characteristics such as color and texture, and we can do a multidimensional analysis. So for that, we can use the feature descriptors such as the color or the orientation or the layout. So various elements we can identify that represent characteristics that represent the image. And when we do that multimedia analysis along the multidimensional analysis for the multimedia, so we may get a kind of the hypercubes up to 3 dimensions. It's easy to represent, but beyond that, it's difficult to represent. But the dimensions, as you can see here, there can be several forms of dimension examples. So in this, these are all mostly related to the picture, but for different other multimedia objects, we need to identify those dimensions and can carry out the multidimensional analysis. And when we are looking for association analysis within the multimedia data, then it can come in several forms. One is that one can be related to the content and non-image content. For example, let's say image, we are dealing with the features which are not represented belonging to the content. So in this case, let's look at an example. What we see, if the 50% of the upper part of the picture is blue, then it represents sky. So what we are doing is that the blue is a feature of the image, but sky is something which has nothing to do with the image. It is just that we are bringing it from outside. We are representing association with such keywords. So similarly, we can say that some picture may be representing a sea, or some picture is representing a car. So for that, we need to define a part of the picture and the characteristics of that, and then we associate a keyword which is outside, which is this is one form of association. And the other one may be that this is association among the contents, but not based on the spatial relationships. So all we are saying is that if the picture is containing 2 blue squares as it happens, and then it may be containing the red circle as well, because that may be the kind of association that we are seeing in our multimedia database. So here we are not talking about whether the squares are on the top or the circle is on the top or they are in the same level, or what is the layout at all. We are not at all bothered about layout. And the third form of association that we can create is that not only we look at the image contents, we also look at the spatial relationships. So in this case, what we'll get is something like, as you can see, if a red triangle is between 2 yellow squares, then there is likely to be a big oval shaped object underneath. So here we are talking about the relation between the squares, the triangle, and the oval object. And we are creating an association relationship within the multimedia object based on the contents and the spatial relationships. And the challenge with respect to some of the multimedia objects, for example, picture, is that a picture can be stored at wide range of resolutions. Same picture can be stored, we know, as a 10 MB picture and also be stored as a 10K picture, depending on the resolution at which we want to store. Now, what happens if there are some features which are available at high resolution, but they're not available at low resolution? So one of the ways, but then as we know, if it is a low resolution pictures, they are of smaller size, it is easier to work with them, because we know that the computing is one of the restrictions is the memory size, and also as we have the larger data, when the processing is going to be complex. So for that reason, we would like to work with the objects of lower resolution. So what we can do is that we can make a multi-step association mining. So first we work with a low resolution pictures, and then we find out the patterns, and then we proceed to higher resolution pictures of the same pictures, and we check up whether those same pattern is continuing or not. And another element of interest in the multimedia or the image data is that many times a recurrent object is treated in a different way than a single object. For example, a picture containing two circles is different from a picture containing one circle. This is unlike the relations that we establish in a normal relational or business data. What happens is that when we say a person buys a gallon of milk, we treat the same way that the person buys milk. Even if the person buys 5 gallons of the milk, we treat the same relationship, that is, buys milk. But in an image, we tend to treat this one circle, existence of one circle is different from the existence of the 5 circles within the same image. And further to that, the multimedia objects have the special relationships. If it is an image data, we have the spatial relationships that showcase the above, beneath, nearby, etc. So we go beyond these the associations, and we also have to use the spatial relationships to do the association mining. And now we look at the spatial mining. So what happens is that, as we can see, even the images have the spatial relationship between them, but there are some data for which the spatial relationship is everything, which is very important. When we are looking at essentially a geographical information system, or when we are looking at a VLSI design, or anything for which, for example, a protein molecule arrangements within the protein molecules. So for us, the spatial relationship is very important. So how things are connected and how they are going to, how far they are, that is going to be the most significant element there. So for that, we work with a spatial data, and it carries some of the elements from a normal image mining, but it has got some additional features or the additional constraints associated. So if you compare the spatial database with the image database, what you see is that the image database will be coming with coming from the satellite sensing or the computer tomography or such techniques, and then we are going to extract the images. But if it is spatial, we generally have the association with the geometry and the geography within there, and we have well-defined extents, locations, and relationships that constitutes the spatial data. And when we are using the geographic information systems, which is a wide bulk of the spatial data, we look for a specific region, and we also do a location analysis to find out if there is a corridor exists or a buffer exists. For example, there are two regions or two locations between which there is a mountain, so that will be a point of interest. And similarly, we may do a terrain analysis or a flow analysis, or we may look at the other kind of spatial statistics, etc., and we may also use the measurements such as the distance, perimeter, etc. All of these elements are particularly important with the geographic information. So when we are modeling the spatial objects, we may take two alternate views. One is that we look at it as a single object. So we are modeling a city, we are modeling a forest, or we are modeling a river, etc. Or we may look at it as a collection of objects. So that is going to describe the entire space. So here we are talking about, for example, we have a country which is divided into states, or we have a land use policy. For example, there is a certain policy with respect to urban land and suburban land, or a rural land, or an agricultural land, or a normal or a fallow land which cannot be cultivated. So in such situations, we need to identify the objects there and then we relate them. And generally the spatial data requires us to look at it as a point or a line or a region. So that is useful in various, for example, when you're representing a geography, a line can help us easy to represent, for example, a road. A region or a area will help us represent a lake. So for this reason, we need these three forms of objects which can express most of the elements that we see within a map or a geographic information system. So we also want to further relate the objects through various techniques. One is that we can relate the objects through a partitioning mechanism, which is saying that one object is divided into two parts. For example, there is a let's say a town where this is the business district, and this is the where people are living. So that is one way in which we can differentiate, or we can partition the spatial information. Or the other way may be that we can create a network. So we can say that there is a town here, there is a town here, and there is a town here. There is a direct road between these two towns, and there is another road between these two towns. So here we are representing the spatial relationships in the form of a network. Or we may further relate them in the other objects, such as the partitions, nested partitions, etc. And we can represent the spatial data in the form of, let's say, for example, here we are doing a partitioning of the space using a data which is representing, let's say, these three types of forest: pine forest, fir forest, and oak forest. We are saying each one of them we are representing using the x and y. So essentially each one is represented as a function of x and y. But we may have an object-based model where each element is represented as a vector. So it can be a point or a line or polygon or any other attribute which we represent in the form of a vector. And when we have a spatial data, we need to look at very specific kinds of generalizations that are there. For example, one of the approach can be that they can be dissolved. So that is what we can see is that this picture, various elements which are somewhat similar, similarity has to be again defined, and then those similar objects have been dissolved into one object. So here we are getting a lesser number of objects, but as you can see here. And similarly, the spatial objects can be merged. That is, these layer 1 and layer 2 has been put together to create a new object. Or similarly, the clipping can be applied, whereby this object has been clipped using this clip layer, and we have got a new object. And similarly, we can have an intersection. We can say take this object and intersect this object with this, then we are going to get a new output. Similarly, we can create a union. So the spatial to spatial kind of operations can be of various different kinds. And when we try to express the spatial data using the association mining, then we may get an association rule which is of this kind, for example, where A implies B with support and the confidence. So it will somewhat come like this. For example, if there is a X represents a large town and intersects a highway, it is likely that there is a water source next to it. So so this way we are going to represent, and here we may have to use the various topological relations or the spatial orientations or the distance information to represent the overall association rules. And like the way we in the images, a progressive refinement will bring in efficiency into the mining task. Even in the spatial mining, the progressive refinement can help. And many times the spatial data is represented as a minimum bounding rectangles. Here, as you can see here, there are main rectangles R1 and R2. And within that, there are smaller rectangles. So we can represent that as a R tree, which is essentially a tree of rectangles. And thereby, we will be able to draw these spatial relationships from this hierarchy more efficiently. For example, when we say that R1 is a rectangle which contains R3, R4, R5, so you know that there is a greater chance of proximity between R3 and R4 compared to R2 rectangle. R2 has R6 and R7. So it is likely that R3 is closer to R4 than to R6. So this type of relationships can be determined using this R tree, which is a rectangle tree, which is constructed using the minimum bounding rectangles. So this can be again a hierarchy, or we can create a tree with the multi-levels, many levels, and that will help us to create efficiently mine the spatial data. Spatial data tends to have one special property, which is correlation. So whenever you have the data which is coming from a neighborhood, it is likely to be related in many ways. For example, when there are two places which are close to each other, they are very likely to have the same level of temperature. So as a matter of fact, you can look at the law of geography. So the things are related, but whenever there is something is nearby, it is likely to be very strongly related compared to the things which are far off. So when you're looking at spatial classification, so given some spatial objects, when we are trying to classify them, what we need to do is that, as we know, for doing a classification which is a supervised learning, we need to have a training data from where the machine is going to learn from the training data, and then is going to apply the learning on the test data or the other data. So what happens is that when you are doing a learning, we are assuming in general that the samples are independent of each other. But then the spatial autocorrelation means that we will not be able to guarantee that they are independent unless we take an extra caution with respect to how we create the samples. So essentially we are constrained with respect to what type of samples we need to use so that we can give the machine the maximum level of information to learn. And similarly, we can do the spatial cluster analysis. We can use the k-means, k-medoids, hierarchical and density-based clustering techniques. And when we do the clustering, we may be able to create the clusters as we are seeing here on the map, which are representing the clusters which represent the various characterizations as represented here. And when finally, let's look at the special characteristics with respect to spatial and multimedia data is that the generalizing them requires us to understand the purpose for which we are working for. So for example, in a spatial data, when we have the geographic points, we want to generalize on various parameters, for example, business or residential or agricultural area or other land uses policies. So we will have a generalization mechanism which has to be input specifically in order for those clustering work. For example, similarly for image data, when we are trying to do the generalization, we can generalize based on various parameters like size, color, shape, such things. And similarly, when we are talking about audio or music data, we need to think in terms of a generalization which is again based on a melody or style, tone, tempo, etc. So for each one of these multimedia data, we need to determine what is the purpose for which we are trying to analyze or cluster or classify or further generalize the data elements to gather the insight.